Chapter 17, Section 5 of your chemistry book. We're going to be talking about nuclear fission and fusion. So what is nuclear fission and fusion? First of all, we're focused on the nucleus of the atom. And fission means a splitting apart. And fusion means a putting together. So we're going to be talking about this. This is pretty new in the last, century or so that we've advanced in this area. And so we're going to talk about how this affects our lives too. First, we're going to focus on nuclear fission. The history kind of goes back to the time when they were bombarding different atoms, especially the uranium atom, with neutrons. And these discovery bombardment reactions led to, in the mid-1930s, Enrico Fermi speculated that bombing uranium element 92 with neutrons might form new elements with higher atomic numbers, and that this didn't exist in nature. So he was actually making new elements, which scientists at first were very puzzled, as Enrico, the experiments were then performed by others. But when scientists tried to do these experiments, they seemed to be contaminated with a common element in each one that was barium. And so this barium, despite all their efforts to keep it pure, this barium kept showing up. And in the midst of this barium showing up, they kind of put it aside. They basically couldn't figure out, didn't really realize that the uranium was actually being split into a barium molecule, a barium element. But it was not until 1938 that a brilliant physicist by the name of Lise Meitner, she lived 1878 to 1968, and along with her nephew, Otto Frisch, they realized what was happening, and they determined that they based their experiments on this German chemist Otto Hahn, that barium was not a contaminant at all. Rather, it was a new type of nuclear reaction that was occurring. The uranium atom was splitting into two smaller atoms. One was barium. And so they named the splitting at this time nuclear fission, correctly deducing that fission was a splitting process and that another product must be krypton. So when they thought, okay, barium and krypton, did these uranium atoms actually split into new atoms? And so they calculate that fission must liberate a tremendous amount of energy. When you split atoms, energy is let off. Remember the strong nuclear force and everything and all the energy, and then splitting this atoms would cause this energy to be beyond what we could even imagine. In fact, 180 to 200 evolts, mega evolts per atom. That's more than 5 million times the energy that's released by a TNT molecule. Huge amount, this chain reaction that would happen. So a chain reaction with a wide variety of nuclides are suitable for a nuclear fission. So here's a picture. The most important naturally occurring fissionable nuclide is, of course, uranium. And it has to be a certain kind of uranium, 235, in the nucleus, which is the protons and the neutrons. So and in the midst of this 235, they could make this happen. So this is a fission chain reaction, as you can see. And of course, its sizes are not to scale, but you have here basically one atom and splitting. As they split, you can see how it splits another one, splits another, and splits another. And this goes many times in just fractions of a second. Another picture up here that we kind of looked at here is the uranium-235. And as the neutron hits it, the neutron approaches uranium, and the uranium becomes unstable there because it's with the 236 as the neutron comes into hits the nucleus here. 236 is the transition state, and so the neutron is absorbed, forming a highly unstable. Now the nucleus is very unstable, as you can see. It's ready to split apart. And then usually out of 6 or 7 absorptions, the excited nucleus immediately breaks apart into smaller fragments, releasing about 180 mega evolts of energy. So you can see how much energy. And as it's splitting, here we have the neutrons, the fission happening in this molecule, splitting out the neutrons. And as they go, we have a barium atom and a krypton atom, 2 new atoms that are, very much filled with the radiation in the midst of this. You're going to get a lot of radiation. So the nuclear fission, a new thing at this time. Of course, the scientists were mesmerized and they started doing more experiments on this subject. We're talking about 1938. This is even before World War II with the bomb. I just think what time. And of course, Lise, a woman, in fact, at this time that was looking at this happen. I bet you're never going to heard her name. So Lise Meitner, or Meitner, that's how you pronounce it, Lise Meitner. But going on, we have to have uranium-235, which only composes about 0.72% of uranium. That is a really rare type of uranium. And this nucleus can capture a neutron from the unstable 236 and break this apart. And we have this going here, and here's the equation for what I just talked about, where we have now, this is how you would write it. Here's uranium-235 with 92 protons. That's the positive then we have the neutron. A neutron hits it with 1 neutron with a 0 charge, and it turns into a barium here, barium here, 139 over 56. This barium right here, 139 atom, turns into that, 139 in the atomic number, or atomic mass number with neutrons and protons, and 56 with the atomic number, which is the protons. And of course we have krypton, the same, with 94 as the atomic mass, and then we have 36 as the atomic number. So krypton, and then you have 3 neutrons, 1 with 0 charge. The bottom number, of course, is the charge, the positive charge. And so we have no charge on this. So it would be, if it was a negative charge, it'd be negative. These are positive, means that they're protons, actually. And so then we go on again now with the 235, and you see here again with splitting again into other atoms, and you see basically the 3 neutrons going, and here you have gamma rays are being emitted and electrons are being emitted. So these are nuclear fission reactions that we're talking about. It says, though there are 200 nuclides of 35 different elements that have been found in the products of uranium fission, the important feature of these reactions is the product of more neutrons. So basically, they're not really looking so much at the element, but that the element can produce more neutrons for more energy, because we want the energy released from it, right? And so they're looking to see which one produces more neutrons when hit, and more neutrons produce other neutrons hit, and then the reaction becomes huge with lots of energy. On the average, 2.5 neutrons are produced by the fission of 1 uranium. So in between that, you have a big chain reaction that happens. And this causes other nuclei to be hit, and so on. And as long as uranium-235 are present, the chain reaction keeps going on, as we see in here, the chain reaction. So now you know what a chain reaction is, you know what nuclear fission is. So let's go on and talk about what is going on with it even today. So first, let's see, okay, the amount of density of 235 uranium is present. So basically, when it says the amount of density, let's go back here, that the chain reaction is going to keep going, but you have to have a sufficient amount of density, right, that's present. And this is called the critical mass. This is going to be a test question, I'm sure. The chain reaction will be self-sustaining as long as the critical mass, the density is present, and that's that critical mass of uranium. So, and each fission will cause at least one additional one, so that enough neutrons would be released to keep the reaction going. So, and they're trying to keep the reaction to go for a significant amount of time is pretty important, because in a huge, when a reaction in multiple seconds, this whole thing could just blow up. You know how that could be, and we've seen that in the bomb. So in an abundantly supercritical mass of highly purified uranium, each fission may cause as many as 2 or 3 additional fissions almost instantaneously, just instantly. So under these conditions, the chain reaction can proceed so rapidly that most of the uranium in the sample undergoes fission within only a few millionths of a second and releases a tremendous amount of energy, and this has caused a nuclear explosion. So in 235, you can have with uranium, you can have this happen so quickly and explode so quickly. And this produces intense heat, X-rays, neutrons from that, radioactive fission, all these products, these different products, gamma rays, all these things are produced in the midst. And so then we talk about the atomic bomb. Let's talk about the atomic bomb. So this discovery had implications, because the world during this time in the early 1940s was headed for a war. And so they were looking then to these scientists. And of course, a lot of the scientists, especially in Germany, as you know, Enrique, as he came here, was Italian, of course, but they were still what was going on in Italy and onto, in Germany with Hitler and Mussolini, that we had a lot of these scientists that came as refugees to America. In this certain group, there were a group of them, Edward Teller, who lived 1908 to 2003, Victor Weisskopf, that 1908 to 2002, of course, Enrico Fermi, who we talked about, from Italy, and then under the direction of General Leslie Groves and Dr. J. Robert Oppenheimer. You probably have heard of Oppenheimer the most, as he, in organizing all of these scientists plus others, they worked together on producing the atomic bomb. Dr. J. Robert Oppenheimer lived 1904 to 1967. We even have movies on him, as he's credited for that, although a lot of talented scientists, and among them Jewish refugees. We see, and Oppenheimer also was friends with Albert Einstein. So here's where we see in the midst, they're looking at this fission process and to develop the world's first nuclear weapon. So on July 16th, 1945, just before dawn, in New Mexico, in the New Mexico desert near Los Alamos, the first nuclear fission bomb, and it was nicknamed Gadget, and it was detonated. It was set off, releasing energy of approximately 20,000 tons or 20 kilotons of TNT from the fission of plutonium-239. Now, when you think of plutonium, you always think, oh, is it plutonium or uranium? Well, plutonium is actually, from the uranium-235, so in the midst of this, plutonium is an offshoot of it. So they're actually, similar in the chain reaction. So a second bomb containing highly purified uranium, this time 235, was then dropped on Hiroshima, Japan on August 6, 1945. And this devastated almost all of the city you can imagine. It was so much energy in this bomb. And then on August 14th, 1945, 5 days later, a third bomb was exploded over Nagasaki, Japan. And then, of course, Japan surrendered, ending World War II. So Hiroshima, Nagasaki came from this investigation. And now nearly all modern nuclear weapons would look towards uranium and plutonium. And now most of them are focused more on plutonium rather than uranium, but in the midst. So here we have pictures here. But here we have a picture of the U.S. Here, the early atomic fission bomb and what it looked like. And you can see the high explosives here, TNT, RDX, barium, whatever, these aluminum shell here, the uranium, 238 in the midst of here, the fission fuel plutonium sphere. So you have the plutoniums here, you have the uranium here. You can see how the high explosive, the aluminum shell, the armored steel case. This was a picture. It was length of 10 feet, 8 inches, and the diameter was 5 feet. So you're talking a little bit bigger than a person, right? And the weight, 2,300 pounds. That's a heavy person. 10,300 pounds. And the yield was 20 kilotons. So we're talking about huge amount of, and of course, a huge amount of energy. Here's a picture here of precisely synchronized electronic detonators. Detonators ignite chemical explosions. So you can see this shock wave that's going through the plutonium. This baseball-sized sphere is only 2.5 times its original density, making it abundantly supercritical. 4 to 5 critical masses. Nearly maximum compression neutrons are to inject to start the chain reaction. You can see in the midst, in a tiny compartment here. You can see this is similar to this down here. And so here's the chain reaction that heats the plutonium up to 50 to 90 million degrees Fahrenheit. And this is in less than a millisecond. So, and this blows the sphere apart. It goes on, the radiant heat penetrates the bomb casing and the heat surrounding, and this forms this fireball and all this radiation that comes into this blast wave, you can imagine, of the atomic bomb. Here's a 12 kiloton atomic bomb test going off here. You can see, you can imagine, out in the middle of the desert. We've had bomb tests in America. They've had bomb tests in, for sure, in Russia. We know that. So, and in other places. So these atomic bomb now, most countries have the atomic bomb. Even now we're worried because Iran, a terrorist type nation against Israel, and Israel has atomic bomb. And so, you know, we're worried about what's going to happen there. And that's actually significant in the Bible, talking about it. Actually, the Bible does talk about a time of nuclear bombs. If you read Ezekiel 38, you can read exactly a picture of what would happen with a nuclear bomb and is going to happen in the midst of this war with Israel. And we know this could happen anytime. And basically, you know, the Bible says, as well, Jesus prophesied that, you know, even in this time, you know, the time would be cut short for the end times because man was ready, had the power now to destroy the world. And so we do have the power now to destroy the world. But we know God is in charge, not mankind. Anyway, that's just a little excerpt. So nuclear power. So now let's talk about the good side of nuclear energy. And that would be nuclear power. So the end of World War II, so the use of nuclear fission now for electrical power production was then pursued. Like, we could use this for the energy, you know, to basically produce electrical energy, right? Instead of using coal, which the world depend on coal for heat and for and onto electricity, so and hydroelectric power and such. That now maybe we could focus on as nuclear power. And so this was pursued. So if a mass of uranium is not highly purified at 235, an atomic explosion cannot occur, even if a critical mass is present. So the mass of uranium had to be very, very pure, because the most common isotope, remember, was only like 0.00, what was it, 0.07%. That's very rare type of uranium. So the other uranium are 238. And so if you put 238 and mix it with it, you're going to slow down the reaction. And so now a more gradual chain reaction. I like to hear the background. We have a lightning storm going on at the same time I'm talking. But anyway, and so now you have a gradual chain reaction that may result in large amounts of heat that are produced in the midst of this, but being very careful of the mixture here. And this being, do we want, how can we control? I mean, basically, how can we control a bomb? That's what they're talking about. So under these controlled conditions, this heat can be used to produce electricity, monitoring by not having necessarily the pure 235. And so in comparison here, it says here, 1 gram of coal produces about 30 kilojoules, whereas that's the energy. Whereas the fission of just 1 gram of coal, 1 gram of uranium produces how many kilojoules? 80 million kilojoules compared to just 30. That's a lot more energy, don't you think? So the fission of 1 kilogram of uranium-235 produces as much energy as the combustion of 2,700 tons of coal. So, and nuclear, basically a nuclear type of energy has no air pollution. And of course, we know the whole world has been polluted in some areas more intensely with the burning of coal. So we would not have the problem there in the midst of, if we could harness this nuclear power. The major difference between coal-fired and oil-fired power plants and nuclear plants is the source of heat for producing steam. So in a coal burning plant, the heat from burning coal is transferred to these boilers or steam generators to produce high temperature steam. Let's look up here. So we have this steam is then fed to turbines, which turn large electrical generators to produce electricity. So instead of burning coal, a nuclear plant produces heat using a nuclear reactor. What is a nuclear reactor? It's a device for safely initiating and controlling a fission chain reaction. So we're going to look at the picture here. So here we have the comparison. We have coal-fired and nuclear power plants here. So, so here we have coal-fired. We have a combustion in a boiler here, and the steam coming through, the steam turbine coming. We have the condenser, the cooling tower, of course. Here we have a cooling tower for coal and fire. And so in the midst, this is to cool everything down. So the boiler comes down here, the steam going through, the steam turbine, the electrical generator, and on to electricity. So this is coal-fired with coal. And so here we have a nuclear plant, the same thing with a combustor and boiler. We'll have a nuclear reactor. And so now again, we still need that cooling power to cool things down. And so we have this condenser here. The water comes through here, same thing. The water comes to cool down. The steam now coming off, the steam turbine, the electrical generator, and electricity. The only big difference here, instead of a combustor and boiler, we now have a nuclear reactor. So this is the difference between, you think, what's the difference between the power plants? Well, not too much except for the main ingredient. So on to, and here we have again, here's another picture as we have a nuclear power plant. Same, this exactly is just showing you how it's reacting and what is needed in the midst. This is our plan, and here is the nuclear power plant. So of course they have the loops that it goes through. Here we have the containment building here, containing with containment of the nuclear. When I say containment, the nuclear reactor is small here, you see. and then the steam generator here. This is all in the containment. One thing, the difference is this has to be so contained because there's lots of radiation, remember? So this is built to contain with a lot of concrete and even the steam and the water and everything that contains it. And as we go here, we have the steam coming through here, the turbines, the condenser. We have the secondary loop here. You can see where the red is the secondary loop going through and the primary loop and the tertiary loop. But as you go through, you can see the path that it takes. And then going through the condenser, as here we have, this is water to replace evaporation from the cooling tower coming up this direction. Really important. The cooling down of this is so important because otherwise the whole thing would blow up. So, and going through, the cooling, here's the cooling and onto the steam turbines and then to the power grid. This is the evaporation in the steam, all the steam and the water coming through here in the cooling tower. So this is how it looks when you look at a nuclear plant. You can see, okay, this is the cooling tower, that big tower you see. Okay, this is to the power. You can see that nuclear reactor in itself is pretty small. And this is, a huge factory, right? So, well, the most important part of a nuclear reactor is the fissionable material used to produce energy. If you don't have the fissionable material, if you don't have the uranium, especially uranium dioxide, this is the primary nuclear fuel. So, and of course, uranium consists of only, uranium-235 is only 0.7%, as I said. 99.3% is uranium, but it's the wrong kind of uranium. So only 235 is fissionable under conditions found in a nuclear reactor. So consequently, the uranium is usually produced then to increase it. They try to enrich this uranium to 2% or 4%. And this makes the critical mass, that mass that they needed to cause the fissionable, to cause everything, the neutrons to go off. So that is very important that they need that much. The key components of the reactor include, okay, what's the components? They have to have the graphite moderator is important. Graphite is important. Graphite moderator, which slows neutrons. This will slow the neutrons down so they can capture them. The 235 uranium has to be captured. And then the coolant. The coolant, like I said, carries the heat out of the core so it doesn't just heat up and melt down. They call that a meltdown. When the coolant cannot cool it off, it will totally melt down. And that's a nuclear accident for sure. And then these movable control rods, and these control rods control the reaction by absorbing some of the neutrons. Very important they have the control rods because now they'd have all these neutrons going off, they could have a bomb, but instead they go through all these control rods which end up controlling so it is the reaction is easy to handle, in the midst of compiling the energy into that energy that we can use for electricity, not a bomb. So anyway, here's a picture here. Pressure water reactor, PWR. You can see here now we have movable control rods here and the control rod. These are the control rods are very important, just to say, because that controls a reaction, as they're called. And here's the water moderator and coolant here in the top. And the warm water is coming in, goes through, hot water comes out to steam, and this is a coolant process. So this is a pressure water nuclear reactor, PWR. Here's the core going through all of these rods and the fuel rods and the steel pressure here, so you can see it's going through. So PWR, pressure water reactor. So going on, nuclear power and the environment. So we're going to talk about the safety of nuclear plants. I think I'm going to stop there because I'm going to go in and describe some nuclear accidents that happened in history, big ones, as Chernobyl. And why did this happen, in Ukraine? But anyway, let's stop there and then we'll go on to nuclear power and the environment.